Welcome to this comprehensive guide on logistic regression. I'm excited to walk you through one of the most fundamental and powerful algorithms in machine learning. Whether you're a beginner trying to understand your first classification algorithm or someone looking to solidify your understanding, this video is for you. By the end of this video, you'll understand what logistic regression is and why it's so important, the mathematical foundation behind it, how it differs from linear regression, real-world applications and use cases, key concepts like the sigmoid function and maximum likelihood estimation, advantages and limitations of this algorithm. Let's dive right in. Logistic regression is a statistical method used for binary classification problems. Despite its name containing regression, it's actually a classification algorithm that predicts the probability of an instance belonging to a particular category. Think of it this way. While linear regression predicts continuous values like house prices or temperature, logistic regression predicts discrete categories like spam or not spam, pass or fail, or buy or don't buy. You might wonder, why can't we just use linear regression for classification? Here's the issue. Linear regression gives us a straight line that can produce any value from negative infinity to positive infinity. But for classification, we need probabilities, values between 0 and 1. If we try to use linear regression to predict whether an email is spam, we might get predictions like 1.5 or negative 0.3, which don't make sense as probabilities. This is where logistic regression comes to the rescue. It uses something called the sigmoid function, also known as the logistic function, which transforms any real number into a value between 0 and 1. The sigmoid function looks like an S-shaped curve and has the mathematical formula f of x equals 1 divided by 1 plus e to the negative x. This beautiful function ensures our predictions are always valid probabilities. Let's start with what we know. In linear regression, we have y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. This gives us a straight line relationship between our features and the target variable. In logistic regression, we take this linear combination and pass it through the sigmoid function, where p is the probability of the positive class. To understand this better, let's talk about odds. Odds are the ratio of the probability of success to the probability of failure. Odds equals p over 1 minus p. The log odds, or logit, is simply the natural logarithm of the odds. Logit of p equals ln of p divided by 1 minus p equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus so on. This is why logistic regression is also called logit regression. The decision boundary in logistic regression is typically set at 0.5. If the predicted probability is greater than 0.5, we classify it as the positive class, otherwise it's the negative class. Unlike linear regression, which uses least squares to find the best fit, logistic regression uses maximum likelihood estimation. This method finds the parameter values that maximize the likelihood of observing the given data. The idea is simple. We want to find the parameters that make our observed data most probable. Let me walk you through how logistic regression works, step by step. Step 1, data preparation. We start with our dataset containing features, x, and binary target labels, y. The features can be numerical or categorical after proper encoding. Step 2, initialize parameters. We initialize our coefficients, beta values, randomly or to 0. Step 3, calculate linear combination. For each data point, we compute the linear combination z equals beta 0 plus beta 1 x1 plus beta 2 x2 plus until beta n xn. Step 4, apply sigmoid function. We pass z through the sigmoid function to get probabilities, P equals 1 divided by 1 plus E negative Z. Step 5. Calculate cost. We use the log likelihood as our cost function. For binary classification, this is cost equals negative y times log of p plus 1 minus y times log of 1 minus p. Step 6. Update parameters. We use gradient descent to minimize the cost by updating our parameters iteratively. Step 7. We repeat steps 3 through 6 until convergence or for a specified number of iterations. Step 8. Make predictions. Once trained, we can use our model to predict probabilities for new data points. Logistic regression is everywhere in healthcare. It's used to predict disease diagnosis, treatment outcomes, and patient risk assessment. For example, predicting whether a patient has diabetes based on glucose levels, BMI, and age. In marketing, it helps predict customer behavior. Will a customer click on an ad, make a purchase, or churn? Email marketing campaigns use it to classify emails as spam or not spam. Financial institutions use logistic regression for credit scoring, fraud detection, and loan approval decisions. It helps assess the probability of default based on various financial indicators. In tech, it's used for recommendation systems, A/B testing analysis, and user engagement prediction. Social media platforms use it to determine which posts to show in your feed. Why is logistic regression so popular? Here are its key advantages. Simplicity and interpretability. The coefficients directly tell us how each feature influences the odds of the positive class. A positive coefficient increases the odds, while a negative coefficient decreases them. No assumptions about feature distributions. Unlike some algorithms, logistic regression doesn't assume features follow a normal distribution. Fast training and prediction. It's computationally efficient, making it suitable for large datasets. Probabilistic output. Unlike algorithms that just give classifications, logistic regression provides probabilities, which are often more valuable for decision-making. No overfitting with small datasets. It's relatively robust against overfitting, especially with regularization techniques. However, logistic regression has some limitations. Linear decision boundary. It assumes a linear relationship between features and log odds, which may not capture complex patterns. Sensitive to outliers. Extreme values can significantly impact the model's performance. Feature engineering required. For better performance, you often need to create interaction terms or polynomial features manually. Large sample size needed. Especially with many features, you need a relatively large dataset. Here are some practical tips for using logistic regression effectively. Feature scaling. While not always necessary, scaling features can help with convergence and interpretation. Handle categorical variables. Use techniques like one-hot encoding or label encoding for categorical features. Check for multicollinearity. Highly correlated features can make coefficient interpretation difficult. Regularization. Use L1 or L2 ridge regularization to prevent overfitting, especially with many features. Evaluate properly. Don't just look at accuracy. Use metrics like precision, recall, F1 score, and ROC-AUC that are more appropriate for classification problems. Let's recap what we've learned today. Logistic regression is a powerful, interpretable algorithm for binary classification that uses the sigmoid function to transform linear combinations into probabilities. It's widely used across industries due to its simplicity, speed, and interpretability. Remember, while it's called regression, it's actually a classification algorithm that predicts probabilities. The key insight is using the sigmoid function to ensure outputs are always between 0 and 1. I encourage you to practice implementing logistic regression on real datasets. Start with simple binary classification problems and gradually move to more complex scenarios. So, when should you actually use logistic regression? Let me break this down for you. Logistic regression is perfect for binary classification problems. Think yes or no, spam or not spam, pass or fail. It's also your go-to when you need probability estimates, not just predictions. Want to know there's a 73% chance a customer will buy? Logistic regression's got you covered. What makes it really shine is interpretability. You can actually explain your results to stakeholders, and it assumes linear relationships in the log odds, which works great for many real-world problems. Plus, it's an excellent baseline model. Always start here before trying fancier algorithms. But hold on, there are times when you should consider alternatives. If you're dealing with complex nonlinear relationships, small datasets with tons of features, or multi-class problems, you might want to explore other options. High-dimensional, sparse data can be tricky for logistic regression. Speaking of alternatives, random forest handles nonlinear patterns beautifully. SVMs excel with complex decision boundaries. Neural networks are your friend for deep learning tasks. Naive Bayes works wonders for text classification, and decision trees offer that interpretability factor. Here's the key takeaway. Logistic regression is often the best starting point for binary classification. It's simple, fast, interpretable, and gives you a solid baseline to compare more complex models against. Remember, don't overcomplicate things. Start with logistic regression, understand your data, then move to complexity if needed. Thank you for watching. If you found this helpful, please like the video and subscribe for more machine learning content. Drop any questions in the comments below, and I'll be happy to help you on your machine learning journey. In the next video, we'll explore advanced topics like multinomial logistic regression and regularization techniques. Until then, happy learning.